We're going to get into the ideal gas law. And so, what our goal is going to be is to know how to use the ideal gas law. So, to begin, if we're going to talk about the ideal gas law, we have to talk about what an ideal gas even is. So, let's compare an ideal gas to a real gas. All right, so when we talk about a real gas, we are talking about our actual real life gases. Ideal gases would be the perfect version of those. So starting off, a real gas can be liquefied and solidified because of intermolecular forces and attractions, meaning that a gas can turn into a liquid and a solid. For an ideal gas, we're going to assume that they cannot be liquefied or solidified, meaning an ideal gas will always remain a gas because they will not have any attraction between the particles. Additionally, real gases cannot be compressed easily because of the fact that these are real particles, which means they take up space, they have volume and mass, so it gets to a certain point where you just can't compress them anymore. Ideal gases can be compressed easily because we're going to talk theoretically for an ideal gas. They'll have a mass but will take up no volume. So, as you can see here, real gases have certain limitations to them, like the fact that they can change phases of matter and the fact that they have an actual volume to them, while ideal gases, we're going to actually ignore those. Now, these little differences in real gases are actually not significant enough to make any meaningful difference to the calculations for it. So from here on forward, we are just going to treat every gas as an ideal gas because, again, these little issues are so negligible that we can actually just ignore them. They're so small and insignificant. All right, so let's get into the ideal gas law. So the ideal gas law relates every single component or measurement of a gas we've talked about up to this point, including the amount of gas, aka moles. So the ideal gas law is given by this equation: PV equals to nRT. So P is pressure, V volume, N moles, R is called the gas constant, which I'll get into in a moment, and T is the temperature. Notice how I specified the units here. The units are very, very, very important to keep track of, and it's all because of this gas constant R. Right, so to make sure that we're keeping an eye on the units, the pressure has to be in atmospheres, volume in liters, moles, mole, and temperature has to be in Kelvin. All right, so we'll see why when we talk about the gas constant. So to talk about the gas constant, we want to talk about Avogadro's principle, that STP, which is again standard temperature and pressure, which means that the temperature is 273 Kelvin and the pressure of 1 atmosphere. 1 mole of gas will occupy a volume of 22.4 liters. So if we have an ideal gas law, PV equals to nRT. Well, by Avogadro's principle, we have a temperature, pressure, mole, and volume. We have the PV, R, and T. Sorry, PV, N, and T. So that means we can solve for R. So if we just rearrange this ideal gas law, R equals to PV over NT. Okay, so let's go ahead and plug in some values. So we know the pressure is 1 atmosphere. Okay, a gas will occupy a volume of 22.4 liters. Okay, this is when 1 mole of gas is present, and the temperature is 273 Kelvin. All right, so taking these values, we get that the gas constant R is equal to 0.0821, and the unit for R is going to be basically the units over here and their whatever is happening to them. So that means atmosphere, liter, per mole, Kelvin. This gas constant R is, like I mentioned, a constant, meaning it's always going to be this value, and it's going to always be this value of 0.0821 as long as the units are atmosphere, liter, per mole, Kelvin, which means these 4 units here have to be the 4 units for the other variables if we are going to use this number. There are variations to the gas constant R, such as 8.314. This is if the pressure is in kPa, liters per mole Kelvin. So instead of having atmospheres, if we were to use kilopascals, we would get 8.314. Okay, So it kind of depends on the units that you're going to be using here. You'd have different R gas constants. But for the majority of these, we're going to stick to this first one, the 0.0821. Okay, so that's going to be a constant whenever we use R. We will have to convert our units accordingly in order to use this. So let's take a look at an example of what this would look like. So in a deep underground cavern, there are 2.24 times 10 to the 6th liters of methane gas present, with a pressure of 1.5 times 10 to the 3rd kilopascals and a temperature of 315 Kelvin. We are interested in knowing how many moles of methane does the cavern contain. So the fact that we're given a lot of information here should kind of point to the ideal gas law being needed. Okay, PV equals to nRT. Usually whenever we're asked about moles or moles are involved, we're going to be using the ideal gas law because this is the only gas law that actually deals with the quantity of moles, quantity of gas changing, or even needed. Okay, so we if we take a look here, we have our pressure, volume, temperature, and of course R is our constant. But one thing we want to notice here, now we don't have to do this because we know there are multiple R values, but because I'm trying to stick to the atmospheres, we're going to just notice this unit for pressure is kPa. So we are going to want to kind of adjust that. Okay, so right now the pressure is 1.5 times 10 to the 3 kPa. And we're going to want to convert that into atmospheres. Again, this is not necessary, but it's better if you just kind of get accustomed to using one unit for pressure, and the better one to use would probably be atmosphere. Okay, so this is equivalent to 14.81 atmospheres. We have our volume in liters, our temperature in Kelvin. We're set. So if we just go ahead and take our ideal gas law, all right, we get the pressure, 14.81 atmospheres, times the volume, 2.24 times 10 to the 6th liters, is equal to, now we're looking for the number of moles, so that means we have to solve for N. Our gas constant R is going to be that 0.0821. All right, so anytime that we use this R gas constant, we're going to try to stick to 0.0821. We're not going to really use 8.314 too much, and this is again just because the pressure unit atmosphere is more common, and we want to get used to using pressure in atmosphere. Okay, times the temperature of 315 Kelvin. Oh, whoops, let me just fix this up here. Meant to put that unit on the inside. Okay, so just rearranging this, we get 14.81 times 2.24 times 10 to the 6th, make sure that decimal is visible, divided by 0.0821 times 315, and we get that N is equal to 1.28 times 10 to the 6th moles of methane. Okay, so it's going to require a little bit of algebra. We want to make sure that we are using the correct units for everything, using the correct gas constant. Okay, but the ideal gas law is not all that much different from the other gas laws here. We're going to use the ideal gas law anytime that we are discussing a quantity of gas, aka moles.